Which month has 28 days? All of them. See, they all have 28 days, some more than 28. Anyways, we are continuing on with conditional statements, section 2.2 in your book. And what is a conditional statement? Well, it's usually, you're very used to them actually. You've seen them before. It can be if this, then that. So if P, then Q. So you're going to see a lot of these symbols of this P and Q. So this P and Q you'll see. And the way we do this in symbols is with the P and the Q. So I will say P, if P, I don't have the if beforehand, I have this arrow after it, right? Then Q. If I were to draw this as a Venn diagram, what if P means is that P is inside of Q. That means, and I always like to say this every year, if I'm standing in P, yes. If I'm standing in P, am I in Q? Yes. If I am standing in P, then I'm in Q. So what is this P and this Q? P is the hypothesis. So it's the starting part of a conditional statement. It's a thing that you are starting with. If I'm standing in the P. It follows the word if. Okay? So if the word if is there, that means that's the hypothesis. Then the conclusion is the part Q. So that means the then part. So it follows the word then. Sometimes the word then is understood rather than written, so you might not always see the word then. Let's go ahead and take a look at a few examples. So example 1, I want you to underline the hypothesis and circle the conclusion for each conditional. So on the first one, a number is an integer if it is a natural number. So here's the if, right? So this must be the hypothesis. If it is a natural number, then the number is an integer. There is your conclusion. The next one, if today is Thanksgiving Day, then today is Thursday. So you see the if there. So that means today is Thanksgiving Day is the hypothesis. Here we have a then. So you can tell that today is Thursday is the conclusion. A number is a rational number if it is an integer. That if is our clue, that being an integer is our hypothesis. Then the rest is the conclusion. You notice that on 2 of these examples, there is no word then. Having the word if can help you identify the hypothesis. Then the other part is the conclusion. In example 2, I want to write a conditional statement for 2 things. We're going to start with this Venn diagram. So the way I always like to start, there's the P. Look, I'm standing in P. If I'm standing in P, then I'm in Q. All right? So if I use the symbols, it's if P, then Q. So if it is a blue jay, and you can use it if you're not feeling very creative on what it is. And then you can say, then it is a bird. So the bird is the conclusion, and blue jay is the hypothesis. There's a blue jay, and there's the bird. Now we want to write a conditional statement for this one. An obtuse triangle has exactly one obtuse angle. So I'm probably going to start with this obtuse triangle. All right, I'm going to turn this into my hypothesis. And then exactly one obtuse angle, that will be my conclusion. I could say if it is an obtuse triangle, but I could say also if a triangle is obtuse. Pretend I can write a triangle. Is obtuse, then, and now I'm getting to the conclusion, it has exactly one obtuse angle. So the hypothesis again is if a triangle is obtuse, the conclusion is it has exactly one obtuse angle. Now, truth values, when we make a statement, you should be able to say whether it is true or false. Now, So with inductive reasoning, it's much easier to prove something is false than it is true. So one of the best things you can do is see if you can make the hypothesis true and the conclusion false. So remember the Venn diagram. What you want to do is see if you can somehow make this P so it's not in Q. So maybe it's actually, let's see if I can move this. Maybe Q, oops, sorry. So maybe it could be more like the P is not entirely inside of Q. So I'll draw you another Venn diagram here. So see here, I could be standing in P, but not in Q. That would be a false. Okay, so let's look at some statements and see whether they are true or false. Determine if each is true. If false, give a counterexample. If one number is even and the other is odd, then their sum is odd. So remember on the last section, we would test these. So let's pick an even number and an odd number, and then we add their sum. All right? You can pick any even number, any odd number, and see what the sum is. We'll say 12 and 23. Every time I added them, was I ever able to get something that wasn't odd? No, I wasn't. Now, you could say try negative, and you still would get an odd. If you try 0, 0 is neither even nor odd, so that won't work either. So this is true. We could not find a counterexample to prove it false. If two angles are acute, then they are congruent. So here are two acute angles, right? Maybe both of those are, what, 20 degrees? Those are congruent. But what if I did another acute angle that was more like 30 degrees, right? That's not congruent to the 20 degrees. I can still have an acute angle that's closer to 60 degrees. So if two angles are acute, that does not mean they have the same measure. This is my counterexample, having a 30 degree and a 60, or a 30 degree and a 20 degree angle. If you multiply an even and an odd number, then the product is odd. So let's say 2 times 5 is 10. Wow, I didn't have to get very far at all, did I? 2, 5, that's 10. That's even. I don't have to keep doing this. I only need one counterexample. So I can say this is false.